right. And we have our final group for the morning. Yeah. Thank you. Who's in charge? All right.
Okay, good morning. My name is Naomi, beside me is Ian, and over there we have Keith, and we are group 15. From the beginning of the semester, we have been working on an inverted pendulum cart for our customer, Dr. Ankit Goel. So a bit of background, Dr. Goel is part of the UMBC MECI department, and he runs the Estimation Control and Learning Lab. For our project, the overall goal is to design a system with a cart and a pendulum attached to that cart that moves linearly over some sort of track. And we were tasked with measuring the cart position and the pendulum angle. So our key system requirements, we have that the system shall have a repeatable method of measuring the position of the cart and the angle of the pendulum. And our angle measurement should be within plus or minus 0.5 degrees, and our position measurement should be within 0.25% of the true position.
So when it comes to the design of our project, it was crucial to choose parts that not only achieve the key system requirements, but also remain relatively affordable. So first up, we have the ultrasonic sensor, and this measures the position of the track of the cart along the track. And it does this by multiplying the speed of sound by the time it takes for the ultrasonic wave to hit the face of the cart. And it's proven to be accurate within a precision level of less than a centimeter to the true position of the cart. We also have the incremental rotary encoder, and basically this calculates the angular data of the pendulum as it swings by converting the rotational motion of the pendulum as it swings to electrical pulses, and these pulses are converted to angular data using the encoder's pulses per revolution value and the total angle per revolution, which is 360 degrees. So on the electrical side, we use the breadboard that allows us for easy prototyping and also reduces the risk of damaging the Arduino. The Arduino allowed us to control our components such as the sensors, the motors, and we also decided to use an Arduino shield which allows for safe and secure connections without soldering the components. So the motor was a very big part that we had to choose. It was a very important component of our design, and we had to choose a bidirectional motor that allowed us to move the cart in both directions, back and forth. And one of the most important factor that we took into consideration was the torque required. And to calculate this torque, we used the force that the motor will require to not only move the cart but also overcome the friction that the gear might have along the track. We also did use a motor driver, the L298N H-bridge, and this allowed us to not only control the direction in which the motor is spinning, but also the speed at which the motor was spinning. Also, for the structure of our design and the frame, we used aluminum 8020, and this provided us a strong, durable support, but also remaining relatively lightweight. And it was also very easy to assemble and disassemble, which was done using fasteners and angle brackets. Finally, for the linear motion of our design, the linear motion of the cart, we used the rack and pinion mechanism, which basically converts the rotation of the motor shaft into translational motion while also staying accurate and was relatively affordable.
For the initial design evolution, we have the structure layout, and the dimensions are 1 foot height, 1 foot width by 3 foot length as per the customer specifications. And this was cost effective using the longer length extrusions, cutting down to the lengths we needed and the strength and appearance that we would need for the 5-pound cart maximum. For our bearing options, these bearings both fit directly on the extrusion specifically. Option 1 is more of a side mounted, which would not be ideal for our components. So we stuck with bearing 2 on the right, which would allow us to mount the cart on top and works better in compression. For our cart designs, we wanted to optimize the reduced rotation on the bearing. So we condensed all the components on top of the bearing, by the final iteration, where the first iteration you can see that the components are mounted very far from the bearing, which increased the friction. For our final design, we implemented the electronics plate for the Arduino breadboard and the H-bridge, and we have the rack brackets to secure the rack to the extrusions and the sensor mount to point the sensor at the cart. This is a motion analysis video. It might play. Well, the gear would spin and the pendulum is affected by gravity, and then you can just see it swinging. For the fabrication, we utilize 3D printing for the accessibility, the affordability, and the fast prototyping it allowed us to do. These are some of the 3D printed parts we designed. For machining parts, we cut down the extrusions, the rack, to the dimensions we needed for the system boundary, and the electrical components that we programmed being the Arduino to work with the encoder, the motor, and the H-bridge. This is a video of how we assembled it. This probably won't play either. So we can show this later if needed.
So for our testing plan, we plan to mount a phone on a tripod to take stable pictures of the entire system with the pendulum at a specific angle or any angle, then upload those photos to SolidWorks and measure that angle and confirm that our Arduino actually runs and gives us the same angle within our tolerance. For the position of the cart, we plan to use calipers to measure arbitrary distances and again verify that the Arduino gives us the values to our tolerance. And for the Arduino program, we plan to run various cycles of the pendulum and make sure that every piece of data that's collected can be referred back to for any analysis needed. So our budget breakdown, we have 3 major categories: hardware, structure, and electrical, and in total we spent $409.87. And here we have our timeline. We could, because we started the project from the beginning of the semester, you can see we allotted a significant amount of time to each phase of the project, including like early development, purchasing, testing. And we have some time at the end of, like from now towards the end of the semester to finish up any testing and analysis we need to do on the project. That is all for you. Thank you for attending our presentation. Any questions?
So the ultrasonic sensor must be pretty sensitive, I guess, with the distances, and the pendulum, I guess, has to be like very precise with the timing. What about, have you had any concerns or issues with delay and time delay on the signals passing?
We did not have any delay, especially for the ultrasonic sensor. Our testing revealed that it was very accurate within less than a centimeter, which was acceptable for our key system requirements. For the angular data, we had to perform a little more test. It was a little less responsive than the ultrasonic sensor. So we're currently exploring the options to see if there's a better encoder or like better options that we can have to reduce the error that we're experiencing.
Just to clarify the end use case for this, so does the onboard Arduino electronics, does this run the entire control system for the pendulum experiment, or is this outputting to like a computer or to another experiment system, and it's just collecting and passing on that data?
Okay, so it's collecting sensor data from the position and the angular data, but actually from our project goal, we're not supposed to implement a controller. So basically, we just had to make sure that these values are being measured and stored so that later on, future students can implement like a PID controller to actually control the inverter pendulum.
Okay, thank you.
You're welcome.
All right, congratulations. So this concludes the morning session. We do have an afternoon session around 1 o'clock. We're going to allow all my, first off, let's give them a round of applause for amazing job. We're going to now proceed to the hallway where the demos will occur. My one-on-one students, thank you all for showing up. Give the students some time to get themselves together. We'll give you all about 5-ish minutes. Is that okay? And judges, if you need to use the bathroom, get a drink of water, of course. And so everybody, take care. We'll be back around 1 o'clock online. So take care and see you soon.
Yep. Thank you.